SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. So now let's go through another important topic, that is the C1 continuous elements, where the approximation function is of C1 continuity nature. So this is very much important in the case of bending problems. We'll take 1D bending problems, where if we just take we take x and then y in this direction, and the bending in the positive direction here. This is we measure as v. This is the loading. So deflection is v, which is a function of x. Okay, so everything taken in the positive direction is taken to be positive. So in the y direction, the v in the upward direction is taken positive, and even the loading q is taken in this direction positive. And there can be many other types of loadings also. Like there can be a concentrated force here, if you want, a P R. So P and M naught are concentrated force and moment. At the end. Okay, so this is the description of the problem, and the equation here is that in the form of differential equation. Is what? EI t to the power of 4 y is equal to q, right? Okay, so this is in, and then there's of course the loading P and M naught, which we can also write it. So we'll talk about the boundary conditions a little later. So this is in the form of governing differential equation. In fact, we know that the moment is EI d square V by dx square. So that's equal to M naught here, and EI d cube V by dx cube. So that's the shear, so which is equal to P at that end. Okay, so those are the boundary conditions. Okay, so either you can formulate it using this, and then you go through the weighted residual approach. Okay, and then you do the integration, and then you do that. On the other hand, there's the variational approach. So this is one approach given the governing case. So in the variational approach, we define a potential energy pi, so which consists of what? M squared by EI. And this is the elastic energy. And then we also have Q times V. So what is this one? This is the work of external forces, which is the distributed force. And then we may also add B times the V at x is equal to L. So that's another thing which we can add later. But for the moment, we just see this one. So these things can be added anytime later. And what is M? So the bending moment at any time, at anywhere, is given as. So all right, so now potential energy so you can put it here and then square it. So there's also, of course, there's a half here. So it is EI d square V by dx square square okay, so this is the potential energy, this is the elastic energy, and then this is the work of external force with a negative sign, so that will constitute the potential. So here now we will convert this V, right? So we have to write. So you take a general element here and then V approximation we have to write. So when we write V approximation here, so what are the conditions on this one? The conditions on this V is that if you look at this integrand here, so what is that? We have here d square. So this second derivative is occurring here in the integrand. So there is a second derivative. In the integrand. Right? So if it is, that's d square. So what does that mean? D square V by dx square. So if you have a second derivative, so that means that your approximation V hat. So whenever you do the V hat, then you should have a second derivative in the element. So non-zero continuous second derivative be existing in the element. Okay, second derivative should exist in the element. So whenever you have this element, so you should be such that the V should be at least what kind of polynomial? You should be at least a second degree polynomial. That's what it is in the element, right? Because d square should not go to thing. Okay, so that's number one. What is the other condition? So other condition is that so d square can have, so as far as the continuity, inter-element continuity is concerned, so d square by dx square is essentially continuous, but at the most can have finite discontinuity at element boundaries. So we discussed this at the time of the calculation or the determination of the stiffness matrices and so on. So if this is so if you have so if D square can have a finite discontinuity, right? So what does that mean? So that means that the first derivative that is dv by dx has to be continuous. So if this is so you can see here, this is dv by dx should be continuous. Continuous like this one, right? So which means that, which is called C1 continuous element. So the approximation here, we had E and we had E plus 1. When you take the derivatives, so you should have the same derivative here. At this point, we should have the same derivative at the common boundary. So if you have two elements like this, so at J, you should have the same first derivative value. So if that is the case, so then if you want C1 continuity, then what is the approximation? So this, if you recall our discussion on this continuity and so on, when we needed a C0 continuity, you remember we used to take the function itself as one of the nodal variables. So here, if C1 continuous is required, so that means that we require the function as well as the derivatives should be, so therefore the function v okay, and the first derivative dv by dx should be taken as nodal variables. So this is important for us. So how do we, so assuming that we have a two-noded element I and j, then what we are saying is that the nodal variables have to be here, or we can call it as 1 and 2, two-noded in the two-noded element. So what we take here is v of 1 and dv by dx of 1, okay, and v2 and dv by dx of 2 at node 2. So these are nodal variables. So the nodal variables are v1 dv by dx at 1 and v2 dv by dx. Okay, so these are 4 variables. So that means that the approximation v should have 4 coefficients in that polynomial. So we always assume polynomial representation, this one. So we take it to be 4. So a1 plus a2x plus a3x square. So we have 4 coefficients. So we'll choose with 4 coefficients here. So equivalently here, and which we would like to convert to the nodal variables. So that means that we'll like to convert that into n1x of v1 and n2x. Here we will write dv by dx as the variable 1 and n3 of v2 and n4 of dv by dx. So this dv by dx is usually very small, and then we also know that it's given the name slope. So here, so dv by dx is small value, and is usually known as slope. Theta. So just for the sake of conciseness, so we can write, therefore, we can also write n1 v1 okay. So this n1, n2, n3, n4 are shape functions as usual. Are shape functions. So how do we find these shape functions? So either you can say that it has a value of 1 corresponding to this degree of freedom and 0 for all other degrees of freedom. So we don't simply say that at other nodes, but we say that degrees of freedom. For example, at node 1 itself, we have another degree of freedom defined, which is the derivative dv by dx or theta 1. So it should be 0 at all. Or on the other hand, we'll also say that since this is Vx is given by this, so we use this equation, okay? We use the equation to formulate 4 equations in the 4 unknowns here. For example, V is equal to V1 at x is equal to x1, or let us just say at x is equal to 0. So at x is equal to x1, so let us say at x is equal to 0, so v is equal to v1, so we have a1, and x is equal to 0, dv by dx is theta 1, which is equal to a2, and at x is equal to, say, h, or instead of L or A, so let's just say L here or H, doesn't matter. Okay, so V at x is equal to L is equal to V2, and so this is A1 plus A2H, A3H square, A4H cube. So similarly at x is equal to H, dv by dx is equal to theta 2, and this is A2, and this is twice A3H and 3A4H square. So this is the usual procedure. So we convert this basic polynomial coefficients into the nodal variables by reformulating them into this equation. So we can write down these things in a form of V1 theta 1 in a matrix equation. A1, A2, A3, A4. Let us just fill it up. So it is 1, 0, 0, 0, 1, 0, 0, and 1 h square, h cube, 0, 1, 2 h. H square. So this is the kind of equation. So converting A1, A2, A3, A4 into V1 theta 1, V2 theta 2. So we can find out these things. So inverting, we get minus 3 by h square 2 by h. Two by h cube, 1 by h square, minus 2 by h cube, okay. So finally, we can write this one as 1 x square x cube so whatever you get A1, A2, A3, A4, you can write it in the, substitute it here. Okay, so this is how V can be written in terms of V1 theta 1, V2 theta 2. So these are the shape functions, right? So they are nothing but the shape functions. Now we can recognize that these are nothing but the shape functions. So I will write it again. Therefore, so we can recognize that N1 is, so I'm just writing it again. So H is the same as L. X minus 2x square by h plus x cubed by square. Three x square by h square So, okay, so these are the shape functions corresponding to V1 theta 1 and V2 theta 2. In fact, if you look at these things, So how these n's are. So if you look at this one, so it has a value of 1 at n1 and it looks like this. This is n1 and n2 is like this and n3 is okay. So these interesting ones are, for example, n1 has a value of 1 at node 1 and goes to 0 at the other node. But it also has 0 slope here and 0 slope here, which means that n1 has a value of 1 and 0 for all other degrees of freedom. What is the other 3 degrees of freedom? The slope at 1 itself is a degree of freedom, and the function value at 2 as well as the slope at 2 are the degrees of freedom. So then it goes here to 0 for both function as well as the slope. So similarly here, this n2 is interesting. It has a slope of 1 because it corresponds to slope 1, and the function value is 0 because that is the degree of freedom, and 0 here both. So similarly for the degree of freedom 3, it has a value of 1 for degree of freedom 3, which is the function value or the deflection at node 2, and the slope has to be 0 here because that is another degree of freedom. So like this, so these are known as Hermite polynomials. So these are higher order to Lagrangian polynomials. Lagrangian polynomial only talked about the function value, whereas here Hermite polynomials talk about the function value as well as the degree of, as well as the derivatives. Okay. So this is how we formulate the function values, various shape functions. So now if you want to find out the stiffness matrix, so if you look at the stiffness matrix, what is that which we need here? So it is K times, what is that? Half. We have the potential energy here. So let's first of all formulate the potential energy, then we go for the, so here half d square v by dx square dx. So how do we get the stiffness matrix here? So that means that we have to calculate the d square y by dx square and then square it. So how do we calculate d square y by, and then we want to take a square of it. So if you look at the d square y, so how do we have v there, approximation with the function. So where we have so we have to write this here. Okay, we'll just stop here for, and then we'll continue this in the next class.